Welcome. In this video, I want to teach you about C++, pointers, and references. But not only that, I want to teach you why they're so essential, why you need them, why you cannot live without them. Sometimes we can get away with not learning some things and just kind of never use them. But if you're going to be a C++ programmer, you have to understand pointers, you have to understand references, because you're going to have to use them eventually. So in this video, we're going to start by talking about why do we need pointers? What is the problem that they're trying to solve? Why you can't live without them? And then after that, we'll talk about how they're structured within memory. So we need to understand how they work so that we are able to understand how to use them. And lastly, we'll talk about how to use them. So most of the video is going to be on pointers. Once you understand pointers, references kind of come for free. All right. So that's just kind of how it goes. So this video will be a little bit longer than usual. However, I am pretty certain that by the end of this video, you should be able to understand pointers and references very, very well. Okay. So let us get started. To understand pointers, first we need to understand the motivation for why we need pointers. So I'm going to write something very simple, very, very small piece of code here. So I'm going to have int, x is equal to 5. That's a weird x. X is equal to 5. And then I'm going to say int y is equal to 7, right? And then I'm going to put a very simple line that you have done many, many times, right? That's not it. I'm going to assign the value of one variable onto another variable. Right? So the value that it's in y will be assigned to x. Now, I want you to put pause for a second, and I want you to think specifically what is happening behind the computer with these two variables. What does it mean to assign y into x? So put pause, think about it for a second, and then we'll keep going. Okay, hopefully you put pause and you put some thought into it, but it's something very simple, but you need to understand what's happening behind the scenes. You see, the value of y is 7, and the value of x is 5. And then the value of y gets assigned into x. However, something happens. You create a new value. You create a new 7 and then put it into x. In other words, the 7 that gets put into x is not the same 7 that you have in y. They're just not the same ones. And so what ends up happening behind the scene is that you get something called copy, right? So the value of y gets copied into the value of x. Now we have two 7s that are completely different from each other. Okay, you might say, fair enough, it copies, so what? Okay, let's explore this a little bit farther. Let's see where else does this copying mechanism occurs. So let's have this function, right? So I have a function here. It's a simple function. It's an add function. It takes two parameters. It has a parameter called x of type integer, and a parameter called y also of type integer. And then somewhere down here, let's say somewhere down here, I have some uses for that function. So I create a variable called a, we assign the value 5, which is right here, and then I have a variable called b that I assign the value 7, and then I pass them to the add function. Now, what you will notice here is that the value of a gets assigned, or I should say, the value of x gets assigned by the value of a, right? So a goes into x, and then after that, the value in y gets assigned by the value of b, so b goes into y, right? So notice we have the exact same theme that we talked about earlier. So the value of a gets copied into the value of x, and the value of b gets copied into the value of y. What I want you to hear there is the keyword is copy, right? So we're copying values from one variable into another. Okay, that's two places where copying occurs. Where is the third place? Well, let's take a look at also the exact same function, but this time, and I have a typo I just noticed, so let's just fix it real quick. I have void, but this should be int, right? So I have the exact same function, except this time the function actually returns something, right? So what ends up happening here is that I still have two parameters, x and y, and I'm still going to pass two values into it, 5 and 7. So the value of 5 gets copied into x, and the value of 7 gets copied into y. But then I return sum, right? So sum goes back. And where does sum go? Goes into r. So in other words, what I'm doing is I am doing something like r is equal to sum. And so what's inside of sum gets copied into r. So I want you to hear again that keyword, copy. So the problem here is that we are copying values from one variable into another. And you might be like, okay, what's the big deal? I mean, it's just copying, right? The computer does copying. It's so simple. However, there are problems that come with copying. What are some of those problems? Well, there's three problems. We can generalize the problems with copying in three ways. The first problem is that sometimes you just don't want to copy, right? Like you have some piece of data and that data you're going to use it. You just want to use that piece of data. You don't want to make copies of it. And if you don't want to make copies, why should the program not give you the option to avoid making copies? And if you're going to be using that value within functions, or you're going to be returning it from a function, or even if you pass it to one function, which then goes to another function, and if it's going to be making copies, you have to then keep track of all the copies. And then you have to know, like, okay, well, which one is the final? I don't know. It gets tricky. So sometimes you just simply don't want to make a copy. The second problem with copying is that some values are just big. Now imagine an array. Imagine you have an array that it's like 100 megabytes. You just have tons of data, and you want to pass that data to a function. And then that function does something to that data, and then passes it to another function, which also does something to that data. Every single time that you do that, you're making a copy of that array. Well, you don't want to make copies of large chunks of data. You have the same problem as the first problem, which is you don't want to copy that much data. But two, now you have to keep track of two large chunks of data, one that's modified, one that's original, and then if you do a third modification, now you have three of them that you have to keep track of. It's too much work. So whenever a piece of data is too big, sometimes if you want to pass it to a function, you just don't want to make a copy. And the third problem is sometimes making copies is complicated. Sometimes, like, what does it mean to make a copy of an object? So we talk about classes and objects here in the channel. Or, well, I have some videos on object-oriented programming. Well, you have a class, you instantiate an object of that class, then what? How do you make a copy of said object? Some objects are pretty straightforward, but some objects are not. Let me show you an example. Imagine that you create a class, and that class is to specify a house. And then you create an instance of that house. So imagine I create that instance. I have a house. I'm not the best person at drawing, but here we have a house and we have a door, right? And not only that, but this house has an owner. And so we have another object which represents the owner. Now, imagine again that you try to pass this house object into a function, and the function is going to make a copy once you pass it as a parameter. Well, now we have a problem, because what does it mean to copy a house that has an owner? So does that mean that you're going to copy that exact same house like over? Like, are you gonna make a copy of the whole house? Let's say that if I do that, are you gonna make a copy of the house the same way with the owner? Like, do you make a copy of the owner as well, or do you not make a copy of the owner? What do? It's something that you have to specify, and it's something that perhaps you don't want to have to deal with, because again, making copies of certain objects, especially objects that contains objects, you have a hierarchy of ownership of objects within this one instance of a class. Well, the problem occurs that how do you make copies of these complex objects, right? I said the word object too much, so it felt like a mouthful. However, I think you understand what I mean, is that sometimes it's very difficult to make a copy of an object, and you have to specify how that copy of an object works. And most of the times, you just don't simply want that to happen. So we as programmers, we should have the flexibility. We should be able to tell the computer if it should make a copy or if it shouldn't. And if it always defaults to making copies, but there are times where we don't want to make copies, certainly there has to be a way for us to go around that. And that way is pointers. Now, before we start talking about pointers, we have to talk about memory. Because if you don't understand how memory works, you could still maybe understand pointers, but you're going to have a vague idea of it. So let us talk a little bit about memory. So when we're talking about memory, we're talking about RAM. You know that thing you would go on the internet to download so you can actually play some games? Yeah, I didn't do that? Okay, well, anyway, you can't download RAM. However, when we talk about RAM, that's exactly where we store all of our data for a program. Right now, you're watching this video on YouTube. You probably, let's say you're on your phone or you're watching it on your browser. All of those programs are stored in RAM. Every time you do anything, it's in RAM. So for us to understand how pointers work and how data is stored in memory, we need to understand how RAM works. So RAM is actually very simple. You can think of RAM as a huge table. So I'm just going to draw this big table right here, just for you to see. And this table has two columns. And then it has tons of rows, okay? It has many rows, okay? The more RAM you have, the more rows you get. 8 gigabytes of RAM, it's 8 gigabytes of rows. 16 gigabytes of RAM would be like 16 gigabytes of rows. That might not be entirely accurate, but you get the point. The point is that the more memory you have, the more rows you get. And the first row, what he talks about is called an address. And the second road is the actual value stored in that address. So when you create a variable, that value in the variable will be put in one of these right columns, so in the value column. And that variable will have a particular address where you can find that variable. Now, addresses, they always follow a pattern of incrementing one by one. So the first address will be 0, the second address will be 2, and then 3, and then 4, all the way until you get to 8 gigs, or 16 gigs, or 32 gigs, or if you have a really good machine, 64 gigs, 128 gigs, etc. Right? But it'll start from 0 and then just keep incrementing by 1. So let's just say, just for the sake of this example, that we start at 100. So here we have 100, and then 101, and of course we have 102, 103, 4, all the way till we get to 105. Now the value that goes in that address, it could be anything. It could be 0, it could be 100, it could be 1,000. If you have a 32-bit system, then the highest value you can put in the value is the 32-bit value. If you have a 64-bit system, then the highest value that you can put here is going to be a 64-bit value, right? So for now, we won't care about that. The only thing you need to understand is that the value goes in one of these squares. So let's just pick some values. So let's say this has the value 0, this has the value 3,000, this has the value negative 2,154, and so on, right? We don't have to go in specifics. But the point here is that this is how memory looks. Okay, how does a variable in memory looks? So I pre-created this memory table, right? And this one, if you notice, we start actually from 110, right? The other one we started from 100. This one we started from 110. The only reason we do that is just to add variety, right? We want some variety. But again, everything starts from 0 all the way to its max value. Now, let's say that I have some variable. So let's say int, and let's just say x is equal to 5, right? How does this map to memory? It's actually not that complicated. First of all, RAM stands for random access memory. And what that means is that you do not get to specify where this X is going to be stored in memory. Who does? The operating system. How does the operating system figure that? It just gives you a random location. That's why it's called random access memory. You don't get to pick. It just says, hey, somewhere in the system, your X is going to be stored. You don't need to know where. The only thing you need to know is that if you ever say, tell me where X is, it'll tell you where it is, but you don't get to say where it goes, okay? It's just how it works. So let's just say that the system comes and says, you know what? I'm going to put X, let's just put X somewhere down here, and I'm going to put its value here, right? So let's say this is X, and I'm actually going to come here and call this X, right? So X is stored in some location in memory. Which location is that? It's going to be at 100. Oops, sorry about that. It's going to be somewhere in 114, right? That's it. So X got some location in memory, 114, and the value of X got put into the value column. And then let's just say, later on in life, because, you're crazy, you want to change the value, you set it to 10. Then what this does is it just simply goes and it updates that 5 and turns it into a 10, right? Fairly easy, nothing complicated. And that's just what it does. Now, not all data objects, not all values occupy the same amount of space, right? So we have the primitives. We have booleans, characters, integers, and floats, right? But then we also have more complicated data structures like arrays, and then if you consider structs, and then if you have objects, some of these values can occupy many, many, many addresses. So for an integer, for example, an integer occupies 4 bytes. And so we can think of each of these little slots right here. So let's just think of each of these little slots as 1 byte, right? So if an integer occupies 4 bytes, then that means that this integer that we have, this X, should occupy 4 slots. So let's just fix this real quick. So instead of me having a 10 just there, we're going to occupy 4 slots, right? Because that's what I'm telling you that an integer occupies. And so now I'm just going to put a big 10 right here. So X, actually, let's also fix this. X looks like this in memory, right? This is how it looks, right? So X has 4 locations in memory from 114 to 117. So this 4 right here. And it has a value of 10. And those 4 slots, we're going to call them X, which is the variable name. Now, what I want you to notice is this left arrow that I have here, right? So this variable X was put somewhere in memory. Again, it was random. However, it has a location. So if you ever say, hey, where is X? So you ask the operating system, tell me where did you put X? the operating system has to give you one address. Now, X occupies 4 addresses. So which address will it give you? Well, the way that the operating system works, the way that it has been established, and I think most systems work like this. There's a chance that some other system might work in a different way, but for the most part, this is the standard. And the standard is that whichever is the first address that the variable occupies, that is the address of the variable. So even though the variable X occupies 114, 115, 116, and 117, the address of X is going to be 114. So X, which is a integer variable, holds the value 10, right? Integer variable, and it is located in position number 14. Okay, that's what you need to know about memory. Every single variable that you create, every single one of them, regardless of the data type. If the data type is a boolean, doesn't matter. Character, doesn't matter. If it's an array, doesn't matter. If it's an object that you created from a class, it doesn't matter. They all occupy a chunk of memory, and the first slot that they occupy, that is the address of that value. And we sort of call that chunk of data the name of the variable. In this case, we called it X. Now that you know why we need pointers and how variables are stored in memory and what addresses are and how they relate to a variable, now we can talk about pointers. So what is a pointer? A pointer is just a regular variable, except that the value that it contains is an address. All right. So the other variables that you've always used, they either contain one of the primitive values, right? So they contain like an integer, boolean, character, float, double, etc. They might be some sort of array, or they might be the instance of a class, some object. Now, a pointer, it is another variable, like all of those variables, except the special thing about it is that its value is an address. And not only it's any address, is an address that points to a particular data type. So you can say you have an integer pointer, which means it is a variable whose value is an address that points to an integer value somewhere in memory. If you have a Boolean pointer, then you have a variable whose value is an address that points to a Boolean value somewhere in memory. Okay, that's all a pointer is. It's just a variable that holds an address that points to some data type, some value in memory. That's it. Okay, so now there's two questions that we have to answer here. Number one, how do we get the address of an existing value? So you create a variable. So earlier we created a variable called X. How do we get the address of that variable? Where is it in memory? I might need to know. I might want to know. I might want to be able to tell another part of my program, this is where X is located. So how can we figure that out? And to do that, we use the address of operator, which uses the symbol ampersand. Okay, so let us jump into code and actually take a look at what exactly is this wholesome operator. So let me just move some things here. So what we had earlier, we had a variable called X, right, of type integer. So let's just type it. So we have int X equal to 5, right? Now I want to know where X is located. And I told you that to do that, we need to use the address of operator, which uses the symbol ampersand. So what I can say is that if I do something like that, ampersand X, that tells me, hey, where in memory is X located? Where in memory is this 5? Now, this is it, right? Like, that's it. Like, you want to know the address of any variable. It doesn't matter what it is. Again, it could be any of the primitives. It could be an object. It could be an array. Well, arrays work a little bit different, but arrays, I won't spoil it. We'll mention it at the end. However, it doesn't matter what kind of value that you have. You do ampersand X, and it will tell you the address of where that value is stored in memory. Now, if you want to see it, why not? Let's just take a look at it. So I'm going to output it. So cout, I'll just say address of X, right? And ampersand X, right? And let's just run it. And what you get here is address of X. And look at these crafty numbers. Like what? That's like 6 zeros, 3A196, FF594. So generally, what the computer does is it represents these addresses in hexadecimal. And so that's why you get FFA and those hexadecimal digits. And so, but basically, this is the address of X. Now, what I want you to know is that this is truly random access memory. So notice the last 3 digits is 594. I'm going to rerun the program. Let's rerun the program. Now it ends in 5D4. It changed, right? Let's run it again. 964. Every time it changes. And so what I want you to know from this is that it's completely random. When you created X and one time that you executed the program, it got one address. You close the program, you run it again. You get another address. You close the program, you run it again. You get another address. Why? Because it's completely random. The computer, the operating system is saying, here you go, man. Just put it wherever. I'm going to put it somewhere, and I'm going to tell you where it is. How? By using the ampersand, or the address of operator. Okay? That's it. Okay, so we know how to get the address of a variable. I mean, it relates to pointers, but we haven't spoke about pointers because I said that a pointer is a special variable that holds the address of some value in memory. So how do we make a pointer? Well, to do a pointer, what we do is we create a variable like we normally do, but in between the data type and the variable name, we insert what we call the indirection operator, which is the symbol of asterisk. It's the same symbol we use for multiplication. So what we have here is I can actually type that again. So we're going to say something like int, and then we're just going to say pointer of x, right? And as I said, we insert an asterisk right in the middle. Now, where exactly you put the asterisk in between these two does not matter. You can put it next to the data type, you can put a space between both, or you can put it right next to the variable name. My preference, just Daniel, I like to do it like that, because this tells me that this is this variable is going to be of a type. What kind of type? Of a pointer type that points to an integer. So as you can see, this variable and the variable above, they look very similar. The only difference between these two is that x holds an integer value, whereas pointer of x holds an address, and in that address there is an integer value, right? So you're kind of, it's like you're telling the person who uses the variable where can they find an integer, whereas x is telling the person I am an integer, right? That's the difference. Is being the integer versus telling someone where the integer is located in memory. That's the only difference. And so this is how you create a pointer. Now, if I do it like this, there's no value, right? I haven't assigned anything to it. So what I can do is I can actually assign the address of x into the pointer of x. So the address of this variable into this pointer variable. So to do that, again, we already know how to get the address of a variable. We do ampersand x. So I can just say equals to ampersand x, right? And so what I can do now is say, pointer of x. I can now do something like this, pointer of x, right? And ideally, these two values should be the same, right? Because we're setting them equal to. So here, we are able to request the address. Here, we're able to store that address as a variable. And then we can manipulate that variable, pass it around, do things with it, as we'll see in a minute. So let's just run it so you can see it. As you can see here, we should put a new line. Let's just do it, right? As you can see, the addresses are the same, right? The address of x, is this hexadecimal number, and then the pointer of x is also this hexadecimal number. So here you have, right? So this is what a pointer is, and you define a pointer by simply putting an asterisk, or I should say the indirection operator, in between the data type and the name of the variable that you're going to use. After that, you can assign any address that you want. If I later have another variable called int, let's just call the other one ny7, and I no longer want to point to x, I can now point to y. Let's lowercase y, and let's just call this pointer, right? And as you can see, this will hold the address of y and not of x, right? So these are different. This is the address of x, and this is pointer, and this is just pointer. So let's just take that off, right? So just so you can see it, right? So pointer, here we have it. Address of x, here we have it. Completely different, because these two are completely different variables. And if you want to see it, because we want to see things, let's just say x is equals to y, right? And then I grab the address of y, and then I show x. Well, these two should still be completely different, right? And the reason for that is because even though x and y were assigned equal to each other, well, we know that what's happening is actually it's making a copy. It's not really talking about the same 7. It's talking about two completely different 7s. And we're trying to avoid copies, and therefore that's why we go with pointers. And in here, there was no copy of 7. Instead, it just gave you the address of where 7 is. So it's still the same 7. Okay, but we're not done. Let's talk more about pointers. How do these pointers look in memory? Let's just take a quick look. So you know how a pointer looks, but we talked about how a variable looks in memory, and this is a special type of variable. The notation is slightly different. So I wonder if it looks different in memory. And the thing is, it doesn't really, but it kind of does. So let me just draw my table again. Now let us throw this x equals to 5 somewhere here. And as we said earlier, we know that the integers, they occupy 4 slots in memory. So let's just make some space here. Maybe there's a faster way to delete these. Yeah, there you go. Oops. Faster way to delete these. Okay, and then we're just going to throw the 5 here, right? And this is going to be x. I'm just going to put the name up here. Now, how does p look, right? So we have p. P is a pointer that points to the address of x, right? It has the address of where x is located. Now, every variable has to be stored in memory. We already said that. Where? Doesn't matter where it's stored. The operating system manages that. It takes care of that. So what I'm going to do is I'm going to show you what it does. So what it does is it's going to say, okay, well, somewhere in memory, I'm going to put p. So let's just pick a place, right? It's random, so I'm just going to pick a place. I'm going to put it here, right? P. And so that's where p is located. Now, what is the value of p? Well, the value of p is what? Is the address of x. Okay, put pause for a second. What is the address of x? All right, I hope you put pause and you thought about it. But we know what the value of x is, right? The value of x is 20. It is the first address that the variable occupies. So what is the value of p? The value of p is 20, right? Now, how do you differentiate this 20 and that 5? Like 5 is an integer, but 20 is an address. They're different data types. Well, the operating system knows that when you create your program, you have defined the data type that your variables are. So this is actually what? An integer, right? And your p is actually an address, right? So whenever you look at the value in here, you say, well, it's a 20, but what kind of value is it? It's an address. Oh, this is a 5. What kind of 5? Oh, it's an integer, right? So that is how you know, that's how you differentiate one data type from another, is you have the data type that that value represents. And the cool thing about this is that, well, because you know that the p is a pointer, well, the value of p is the address of the thing that it's pointing to. Well, it's going to be that 20. So technically, this is why it's called a pointer, right? You can imagine this arrow as the thing called pointer, right? So p is that red arrow that tells you where the value is. And so the cool thing about it is that that's how pointers work. It's that in memory, it's just telling you where to go, and you follow that arrow, right? So if p is here, then you go there, right? And then if you created another variable, let's just let's make this mess here. Hopefully it clicks better. Let's just say we make another one, and this one we call it q, and we set it equal to p, right? P is a pointer. So what is the value of p? 20, right? It's right here. The value of p is 20. It's right here. So now we're going to put it in q. And since we don't have space, I'm just going to put q at the bottom. So this is q, which is going to be an address of data type as well. And the value of it is going to be what? It's going to be 20. And that 20 also points to the same location. So you can have many pointers pointing to the same address. All of them just going to 5, going to x. And that's beautiful, right? You don't have to do anything else. So now you know how to create a pointer, how to assign a value. You know how it looks behind the scenes in memory. How do we actually use them, right? Because we want to use them. It's not that we just want to create them and they're just there. No, we want to use them. And what I want you to consider is that there's a reason why all these locations in memory are completely random, and we don't really care about them. The reason we don't really care about them is because we don't really care where the memory, or sorry, where the values are located. The only thing we care about is to know where they are located so that we can use them. So how do you use the value that a pointer is pointing to? So here, let me delete the y. So let's go back to our code and delete the y. And I'm just going to go back to x, right? Now I'm going to delete this. And so we know that if we want to show where pointer is pointing to, we just simply show its value, right? Because its value is the address of this pointer. Now, what if I wanted to show what is the value that it is pointing to, right? What is it pointing to? It's pointing to x. What is the value of x? 5. So what if I want to show the value 5, not from x, but from the perspective of pointer? Well, to do that, I also use the indirection operator. So I can just do cout pointer value, or pointer, not pointer value, value that pointer points to. Sounds like a mouthful, but that's just kind of how it is. Let's put a new line here. And this is going to be, it's going to be pointer. However, we want to say, give me the value that you're pointing to, not the address of where that value is. So to do that, I put the asterisk. And this is what confuses a lot of people. They don't know when to put the asterisk. Sometimes I remember when I was learning this, I got to a point where I had like 3 asterisks. It was a mess because I didn't know what the hell I was doing. However, the asterisk, sorry about that. The asterisk, all it does is it's telling you, instead of telling me the address, tell me what is at that address. And that's it. So what is at that address? It's 5. So we should have the weird address and then the value 5. So here's the weird address and here's the value 5, right? And that's about it, right? This is it. In a nutshell, this is all pointers are. Pointer holds the address to some value in memory. If you want to know the address, you simply use pointer like any other variable. If you want to use the value that it is pointing to, then you simply put the asterisk and it'll say use the value that you're pointing to instead. That is it. Easy peasy. Like, it doesn't get any easier than that, all right? However, it can get a little bit more complicated. You see, pointers are stored in memory, right? And a pointer is a variable that has a value. And we were able to get the address of a variable and store that address in a pointer, right? And so what that means that if a variable has an address and a pointer is a variable, the pointer also has an address, which means you could have a pointer that points to another pointer indefinitely, meaning a pointer that points to another pointer that points to another pointer, and so on. Now, I don't want to get you confused, but I want you to understand this. So, just to see it real quick, let's take a quick look. So, let me draw my awesome memory table again. Okay, so don't let what I just drew intimidate you. We'll go step by step. So, we did what? We did a regular variable, int x is equal to 5. Okay. Then, we created a pointer variable, and we called it p, right? And we store the address of x, right? Then the next thing looks crazy, right? Because what it has is 2 indirection operators. So it says integer asterisk asterisk. What does that mean? A pointer of a pointer, right? A pointer that points to another pointer that points to an integer. So however many asterisks you have, that is how many levels of pointers you have, right? It'll get a little bit clear once we draw it. But all I want you to see is that what this variable called pp, and I use that term for pointer, is a pointer that points to a pointer, which points to an integer. That's all it is, right? So for every asterisk is a pointer. And that pointer, that pp, points to the address of the first pointer of p, right? So let us just do it real quick here on our table, right? Now we know that integers occupy 4 slots, but I'm just going to occupy 1 for the sake of simplicity. So let's say that x is here, right? So 5 is here, and this is x, right? And then let's say we put p somewhere. Well, let's say we put p right here, right? And what is the value in p? Well, the value in p is the address of x. What is the address of x? The address of x is 51. So the value would be 51. And then pp will be put somewhere else in memory. Let's just put it all the way down here. P. What is the value of pp? Well, the address of p. What is the address of p? Well, the address of p is 53, right? So the value here will be 53. And so what I want you to realize here is that if I ever use x, I'm going to get 5. If I ever use p, I'm going to get 51. But if I say, give me the value that p points to, I'm going to get 5, right? I'm going to go up and use 5. And then if I say, what is the value of pp? Well, that's going to be 53. But if I say, what is the value that pp points to? Well, that's going to be 53 at 51. But then if I say, well, what is the value that pp points to that then it points to? Well, that's going to continue the chain to the next level and give me 5. And so if just to show you real quick in code, if I create another one and I just say int, pointer, and this is going to be the address of pointer, right? And I wanted to use the value 5 from pointer, well, I would have to, first use pointer, right? And use 2 asterisks. And then let's just say, let's just put another line here. Oops. let's just put another line here, and this is going to be pointer, pointer, right? Value that pointer points to. Let's just say, value that pointer points to, right? And so this should be pointer, pointer, right? So this will be the address of the first pointer. This will be the address of the second pointer. And then this will be the value from the perspective of the second pointer of where that second level of pointing is. So let's just run it. And there you go. See, we get the 5 there, right? So for every pointer, every level of pointing that you will have an asterisk, right? So this is a level, I'm gonna call it a level 2 pointer. It points to a pointer, which points to an integer. And again, the data type doesn't matter. All of these, I could change them to booleans, bool, 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 unless this could be true, right? And then if I run this, all I'm gonna get is a 1, because true is equivalent to a 1 once you output it into the terminal as an integer, okay? So the data type does not matter what it is. You use it the exact same way. The only thing that matters is that you understand that once you are dealing with multi-level pointers, that's what I'm calling them. I'm not sure if that's the proper term, but once you're dealing with those, that if you are trying to get the value that you are pointing to, well, you have to use the number of asterisks that your variable is pointing to, right? You rarely use this. You will use this probably when you deal with arrays, more than likely. Other than that, you probably won't need them, although it is possible that you could. But almost certainly always will be this that you will be using, not this. But you should still know about it. And honestly, after learning this, you can sit down, draw the table, and you can do like 3, 4, 5 pointers and just see if you can figure it out. It's a good exercise to be able to understand exactly how the pointers work. Okay, let's wrap up with pointers and then we move on to references. Again, references are cake once we understand pointers. But let's wrap up pointers. So back to square one. So look at what happened here, right? So at the beginning, we created 2 variables, x and y. Then we assigned y into x, and then we said that that was a problem. And the problem was that we were copying values. Now here, we do the same thing, except that instead of x and y being a regular integer variable, now it's a pointer integer variable. And then we assign them equal to each other. And what happens here is that we also, again, get a copy. So now you might be like, bro, you just spoke for like 30 minutes or more, and you at the end we're still making copies. There's a catch. So you see, addresses are always the same size. So you could be pointing to an integer, a boolean, a float, an array, or an object. The size of the address is always going to be the same. So it is better to copy an address, which is very, very tiny, as compared to the data that it is pointing to. And so even though we're still making copies, it doesn't matter, because a copy, it is the smallest copy you can possibly make as compared to copying the actual value. And since we're not copying the actual value, we don't have to, we actually solve the 3 problems that we initially had. Number 1, sometimes we don't want to make copies. Well, we're not making copies. We're making copies of the address, which is okay. We don't care about the address. 2, if it's a large data set, we don't want to copy the data set. You're not copying the data set. You're copying the address. And 3, some objects are hard to copy. Well, you're not copying the object. You're copying the address. So we solve all 3 problems by simply having pointers. Ain't it beautiful? Pointers are great. I know you're gonna love them. It takes time, but once you get to them, you're going to love them. Okay, now let's go to references. Why references? You don't hear about references in other programming languages. I don't think you do. But why references? Why do we care about them? You see, we just sometimes like shortcuts. All right, we want to make some formatting to look more beautiful. We want certain standards to look more elegant. So references are there just to make some pointer uses a little bit look more elegant. Okay, sometimes we just don't want to deal with asterisks and doing all these things to avoid copying. So we created, or well, not we, but someone clever created what they're called references. And honestly, it's just kind of a shortcut. All right, it's a shortcut to avoid dealing with pointers. And since a lot of people don't like pointers, references, they're great. Okay, so what is a reference? References are just like nicknames to a variable. So let's take a look at our table, right? So here I created the table again, and I already created it. You don't have to see me draw it. And here we have a variable called p with a value 5. and this variable P, it is at location 114, right? That's its address. Now, imagine that you say, you know what? I don't mind P, but I would like to have another variable for the exact same location, like another variable name for it. What if instead of P, I'm just going to call it, let's call it T, right? So how could you do that? How can you give the same variable or the same value in memory another name? Well, that's what a reference is. And the way you create a reference is very similar to the way you create a pointer. When you created a pointer, you inserted the indirection operator between the data type and the variable name. To create a reference, you use the ampersand, right? The address of operator in between the data type and the variable name. So if I wanted to create T and T talks about P, the same value in P, the way I would do it is I would just write int, and then I would use the address of operator, and then the name, the new name, the nickname that I want, and I would assign it that variable that I want to share that value with, and I will call it P. Okay? Now, whether I use T or P, it doesn't matter. They both will talk about, whether it be T or P, both talk about 5. Let's take a quick look at code so you guys believe me, right? So here we'll go with let's just use the same thing, T and Y. So I'm not gonna use bool, I'm gonna use int. Why not? Int is equal to 5, and we're gonna do int Y is equal to sorry, we're talking about references. Remind me. And no, we're gonna call this X. I'll show you why that was an error. All right, so now let's delete all of this. Okay, so now what this is saying is that both X and Y are variable names for the value stored in X, right? So X is the primary name, and then Y is a nickname to X. So if I come here and I show cout X, and I do X, and then let's just skip a line, and then cout, let's do Y, and we're gonna show Y, right? We're gonna get that both are 5. X is 5 and Y is 5, right? But now if I change Y, let's just say I say Y is equal to 10. Before they were references, when it used to be like that, X will remain as a 5, and then Y will become a 10. But because they're both talking about the same value in memory, when you modify one, you modify the other, okay? Because they're nicknames to the same value in memory. So when I set Y to 10, both changed to 10, right? So I changed both. Really, I'm only changing one, but it looks to us that we're changing both X and Y. But that's all it's doing is it's a reference, it's just a nickname to the same value. If I remove the ampersand, right, just to go back and show you, one would change to 10, but not the other, because they're two separate values in memory. You know, one is up here, the other one's up here, the other one's down here. But because I'm using the reference, I'm actually saying, you know what? No, they're both referencing the exact same value in memory. That's what a reference is. That is it, right? So if you didn't want to make a copy of X, but you wanted to have another variable for X and not make a copy, you would use a reference. Now, if you didn't know about reference, you would have to create a pointer, and then the pointer would have to get the address of X, and then when you wanted to use the value that the pointer points to, you would have to remember to use the indirection operator. Too much work. So they said, let's do references, and we'll make life easier, much more beautiful. We don't have to worry about asterisk. We don't have to worry about those things. We just simply use the variable or this nickname or this reference like we would normally use any other variable. And that's it. So the reference is really just there to make your life easier and allows you to avoid all this mess with pointers, okay? Now, you might say, Daniel, what the heck, man? You spoke for like 40 minutes when you could have just taught me about references, and I don't have to ever deal with pointers. Well, you see, the problem with references is that you can't do everything that a pointer can do, all right? You just can't. We'll talk about that in a second. But what I want to show you here is what is the power of reference? Where will you use references the most? And so here I have another function, right? It's the same add function, but and you know, because of the power of copy paste, I copy pasted the same mistake that I did earlier, but this should return an integer, right? Now, what I want you to realize as compared to the previous function is that this actually takes a reference of 2 integers, right? And so what it's doing here is that A, right? A goes into X and B goes into Y. But it's not a regular variable, it's a reference, which means what the function is doing, it says, hey, I am going to use the value that you passed to me, and I'm going to use that one. I'm not going to make a copy. I'm going to use that one, and I'm going to give it a nickname so that I can use it internally. I'm going to call it X, and then same thing for Y. So in here, what's happening is that both A and X are talking about the same 5, and both B and Y are talking about the same 7. And so if you modify the value within the function, you're going to modify the value that it came into the function. And so this is one way that you can use to modify values outside of values that were created outside of the function inside of the function, and also how you can pass a value from outside the function to inside the function without having to make a copy. It just takes it in as a reference. It just takes it in as a nickname. So you avoid copies. And again, you might be thinking, then why did we talk about pointers? Because the problem is that pointers cannot always do everything. Pointers can do everything. References cannot always do everything that a pointer can do. So what is the point of a reference? 100, not 100, let's say 99% of the time, you will use references only when passing values into functions, all right? And those values come from regular variables. When will you use pointers? Well, when your original variables are pointers. You cannot go from a pointer to a reference, okay? If you create a reference to a pointer, what is a reference to an address? It just gets like weird. Like you're making references to addresses. You can do it, nothing's stopping you, but why would you, right? The whole point about using the reference is to avoid copying values. And if you're already using pointers, why would you mix the two? So don't mix the two. However, when your original values are in pointer form, then you can use reference. You have to go to pointers. When would that happen? Well, we're not talking about it in this video, but if you ever create a value with a new keyword, what you get from that is a pointer. So if you have values that you have created with the new keyword, you have no choice, but you have to use pointers. There's no option for references. The other time when you need to use pointers is with arrays. Arrays, even though they have a unique formatting as to how we create them in code, at the end of the day, they're pointers. Okay, an array is a pointer. It points to an array of values. And so when you try to pass arrays from your code into a function, you have to go also with pointers. So pointers, you can't eliminate them, but references just makes your life easier to avoid having to pass some things as pointer and avoid all that asterisk and remembering to use indirection operator and all this address of to get the address and all those things. You can avoid that with the simple regular variables. But once you go into the pointer world, you have to stay in pointer form. No reference. Okay, that's the difference of the two. And just to show you as a last slide, this is where you get the 3 famous passing values into a function by 3 different forms. You can either pass by value, which is the copying mechanism, right? That's the downside of it. It makes a copy. You can pass by pointer, which makes no copy. That's great. However, it looks uglier because you have to remember to use the asterisks when you're using these variables inside the function. And number 3, you can go by reference, which uses the address of operator as a reference. And the great thing about it is that you don't have to remember to use anything within the function to use the value that it's referencing to. So it is prettier and you don't make a copy. So this is the winner for most of the time when you can use it. When you cannot, well, this is the second winner. And if you don't care about copies, like honestly, if you're just like passing a regular value like a Boolean and you're like, who cares if there's a copy? Then you go with the old ways of doing it. Okay, I'm not saying to pick one or the and then eliminate the others. All I'm saying is you need to learn all 3, and all 3 have their place and their purpose. So just know that you can do all 3 of them, and they have their pros and cons. Okay, so to summarize this video, just a summary, right? Maybe you skipped to the summary. Why didn't you watch me talk for 40 minutes? What's wrong with you? But if you did, thank you for staying. So pointers exist to avoid making copies, okay? That's the big problem before using pointers. Copies, we don't want copies. We want to avoid making copies, so instead we make copies of addresses, okay? A pointer is just a regular variable, except that its value is an address that points to some value in memory, to some other value in memory, okay? Pointers can point to other pointers, and that's where it can get very interesting. I really encourage you to do that as an exercise. You sit down sometime and just mess with like a quadruple pointer and see if you can get that down back and forth. If you can do that, man, you are set or woman, you are set for life. You don't even have to worry about it. Okay. And references exist there to make your life easier in some scenarios. In particularly, if you're trying to pass values from one place into a function, and you don't want to make copies, so you just simply use references. You can't use references for everything. However, when you can, take advantage of them, use them. I use them all the time. Okay, all the time. All right. Now, here's a few things that we have to talk about before we wrap up. I didn't say everything that has to do with pointers. There's a few things that we will still have to explore. This might be great for another video, but they're not essential to understand pointers. One is pointers using the new keyword, right? So we understand how to get pointers using the address of operator, which gives us the address of a variable that we have used in our code. But you can also create values using the new keyword. And we know that the new keyword returns to us an address of where that value was put. So that in its own could be a whole video to explain the difference between the two types of pointers that we get. I mean, we use them the exact same thing. Everything you learn in this video applies to them, but there is some differences, which if you want to know everything about pointers, I guess you would have to learn that as well. Multidimensional arrays. I say that an array is a pointer. Well, what if you have a 2D array, 3D array, 4D array? What if you have an array of pointers? Yeah, that's where it gets good. You have an array, and then each value of the array is a pointer that points to something, right? Once you understand the multi-level pointers, this is a next exercise. You can get really good with these pointers by using these exercises. And the last thing, which is not something that you essentially need to know, but you should eventually learn if you're in your quest to be a really good C++ programmer, is that you will have to learn about smart pointers, which are pointers that help us manage pointers that were created with the new keyword. So those two topics are not necessarily needed to understand how pointers work, but they're essential to add them to your toolkit because they're used in industry and they're great, and you need them to do certain things that you can't do without them. Okay, so with that being said, that's it. That's the wrap up for this video. I really hope that it really helped you understand pointers and references. It's really important to understand why some things exist. Okay, if you don't understand their motivation, you kind of, you're like, oh, can I just live without them? No, you can't. You need them. Two, I hope you understand a little bit about how memory structure works behind the scenes, how all these things work. And three, how to use them in code, right? We went through some very simple examples, but these simple examples really show how you can use them in any other scenario, whether that be, again, the primitives or some crazy objects that you have. And lastly, how references work and how they're great, and you can use them when you can get away with not using pointers. All right. If you really liked this video, if you enjoyed it, if you learned something new and you don't mind, leave a like. If you are new to this channel, check out the channel, man or woman. And if you like what you see, subscribe. Be safe and peace out.